So today I am going to continue the story from last week. We left off with a brief introduction to Einstein's special relativity. Today I will get into his general theory of relativity, which is probably what he's best known for. This right here is a, does anybody recognize this black hole?
Yes.
Interstellar, yeah, Gargantua. It's actually a very, very accurate rendering of a black hole. Kip Thorne worked directly with the visual effects artists to properly model, using full numerical relativity, what the accretion disk, what a glowing accretion disk around a black hole would look like to an outside observer. So they spent months and months and months and months and months of computer time to generate the images that are in Interstellar, and they're very accurate. There's actually scientific papers from that partnership that they wrote on visualizing things in general relativity. It's very cool. All right, so just a quick reminder of where we left off, for a very, very, very quick summary if you weren't here last week. We had the Michelson-Morley Experiment. Michelson down here, alum of U Chicago, very famous guy. He showed that light can travel in a vacuum, despite what many physicists thought at the time. They thought that waves have to travel in some medium. Sound waves travel through air, water waves travel through water. That light had to travel through a medium. And they called this the ether, and they were always in search of this ether. They were trying to experimentally prove that this ether existed and what its properties were. The Michelson-Morley experiment, originally designed as an experiment to detect the ether, to show once and for all that that ether is there, found that it actually wasn't there. And it found it in successive experiments that Michelson did with more and more accuracy. They proved that there is no ether. And it really raised this question of the notion of an absolute space and an absolute time that's inherent with Newtonian mechanics, if that's really true, if that's really the world we live in, where there's this absolute space that everything is moving relative to. When we had this ether idea, it was a natural thing to think about everybody's velocity with respect to. Once there's no ether, then who's to say that we're sitting still and the sun is moving, or vice versa? So Einstein came forward with his special theory of relativity, and he said that light is a constant speed. The speed of light is fixed for every single observer, no matter how fast they're moving. And that speed of light is an ultimate speed limit of the universe. Nothing can travel faster than the speed of light if it ever travels slower than the speed of light. There's actually a weird idea that if something is in special relativity, it's entirely okay for something to travel faster than the speed of light. It can just never travel below the speed of light. So there are things called tachyons that sci-fi movies love to talk about and make weird things happen with. But everything that we can experience are not tachyons. We are all traveling slower than the speed of light, and we always will. So Einstein came forward, special theory of relativity. There is no absolute space, no absolute time. Everything is relative. And the Michelson-Morley experiment was a major motivator for the success of that theory. Just from those assumptions, just saying that light travels the same speed for every observer has some interesting consequences. That's where we get this time dilation that I mentioned briefly last week. When you move close to the speed of light, your clock will start ticking at a different rate than somebody that's moving stationary, or than some other observer that's moving at a different velocity. And that was experimentally verified in 1972. Some guys down here came up with a great way to get their flight paid for by grant money, and they took a bunch of atomic clocks up in planes, and they timed them and compared those clocks after flying around the world in each direction to clocks on the ground, and they verified that those clocks ticked at a different rate when they were flying around the world. So to take it back for a minute, again, so I said this last week, please don't hesitate to interrupt me at any point if you have questions, and if we start getting too slow, then I'll ask for things to be delayed till the end, but don't hesitate to ask questions along the way for now. The general scientific method that people usually follow in science is we have an existing theory. It describes the results of experiments that have been done so far very well. But then some new experiment happens. It makes a measurement that's not consistent with existing theories. So then theorists develop a new theory that both explains the old one and explains the new results. And if it can successfully do that in a simple way, then that's the new theory. And that's what will go forward, and then the process repeats. Eventually some new experiment will probably come along, find some experimental result that's not consistent with that theory, and then we update that theory. So this is the typical way that theories come about. This is kind of how special relativity behaved. There were these inconsistencies, like the Michelson-Morley experiment, with the existing theory of the ether, and Einstein proposed a new theory. It explained the results of the Michelson-Morley experiment, and it was now accepted as the new scientific theory. General relativity kind of broke that mold. It's rather unique in that there were no experimental results at the time of Einstein's dreaming of general relativity that demanded this theory existed. He really came up with a theory to explain things that didn't really need explaining, but that he thought just must be true because he had such a strong physical intuition, an unprecedented physical intuition. So in 1915, the time that Einstein proposed this theory, there were no experimental results that demanded it. It's pretty unique that that's the case. So the motivations that Einstein actually had, he wasn't motivated by weird experimental results. What he was motivated by was, one, a seeming inconsistency between Newton's description of gravity and his new theory of special relativity. He felt that gravity should also be relative. And so that was one of his motivations. That could be done with a simple modification to gravity, just a scalar, what they would call a scalar theory of gravity, within the framework of special relativity. And that's what a lot of physicists were working on after Einstein's theory of special relativity. They were just trying to basically duct tape a few things in Newton's description of gravity to make gravity now consistent with special relativity. But Einstein, even though those were properly explaining measurements at the time, he didn't like that idea. He thought something bigger was needed. And so just a quick timeline of the progress that Einstein made to general relativity. It wasn't like his theory of special relativity where he just tossed a paper out into the world and said, this is my new theory of special relativity. There was really a progression and a series of papers that really led up to the complete picture of general relativity as we know it today. So 1905, that's when Einstein's special relativity was put forth. In 1907 were the first papers that were starting to lead to this idea of general relativity. And I'll go into what all of these things are in a bit. But the equivalence principle and gravitational time dilation and redshifting of light due to gravity was one paper they had focused on in 1907. And 1911, he put out another paper talking more about the equivalence principle and some of its implications, and then also the deflection of light by massive bodies. And finally, in 1915 is when he put forth his full theory of general relativity and really painted the whole picture that he had in his brain. So the equivalence principle is kind of starting to go in that direction that Einstein thought physics should go. He wanted to make gravity relative, and so his equivalence principle claimed that free-falling frames are inertial frames. So remember, special relativity only applies to things that are in inertial frames that aren't undergoing acceleration. And Einstein said that free-falling frames, so somebody jumps out of an airplane and they haven't reached, you ignore drag from wind, they're in a inertial frame. And that was something that hadn't been said before. And then special relativity applies to those free-falling observers. And so the way you can imagine that is, this is the kind of cartoon picture of how orbits work. If you imagine some big cannon launching a cannonball with a bunch of different speeds, if you launch it slowly, it just falls to the ground. That's free fall motion. If you launch it harder and harder, and eventually with enough velocity to go around the Earth, that's still free falling, but that's in orbit now. And we imagine orbit, we imagine astronauts in the space station in a gravity-free environment. And it's not that they're too far from Earth to not experience gravity, it's just that they're constantly in free fall around the Earth. And so parabolic trajectories that aren't in orbit, but that just follow the trajectory, the ballistic trajectory, if you will, of a cannonball being launched. This is inside of one of NASA's planes where they take astronauts to simulate weightless environments for very short periods of time by having a plane fly in that ballistic trajectory. They experience a very similar environment to people in the space station, which are also in free fall, but just in a much more long free fall. Any questions so far? Yes?
Weren't there some unsolved problems from Newtonian gravity, like the orbit of Mercury?
Yes.
Something that motivated Einstein, but didn't he resolve a few outstanding problems?
So I will talk a bit more about the precession of Mercury's orbit, but it's true that that was an anomalous measurement of the orbit of Mercury at the time Einstein was dreaming up general relativity, but Einstein was fairly unique in thinking that that was actually a problem. The measurement was such a small deviation from what was expected that many physicists believed it wasn't actually a breaking of any theory. It was just some bias in the measurements that would eventually be hammered out. Yes?
That diagram you showed, that's basically the diagram like Newton had in Precession.
That's right. That's right. This is just an updated digital copy of that diagram. That's right.
Can't be.
Go through the timeline again. All right. Okay, so that first bullet point that I mentioned, the first paper of Einstein's after special relativity in this realm of physics, was talking about, in part, gravitational time dilation. And so special relativity kind of put forward this concept of time dilation that was due to things moving close to the speed of light. In 1907, Einstein made for the first time, this claim that this time dilation also happens due to gravity, and that time will pass faster or slower for people in different strengths of a gravitational field. And so particularly, strong gravitational fields will make time pass slower. So as you get closer and closer to the surface of the Earth, you're traveling deeper and deeper into its gravitational potential, and your clock starts to slow down. So this was also verified in that 1972 experiment. I said that the time dilations that they measured were exactly consistent with relativity. I didn't say which relativity. It's actually both relativities that they're consistent with. So there's a time dilation effect that they measured from traveling fast, from having these airplanes travel not close to the speed of light, but close enough that they could actually measure it. And there's also a time dilation effect from being in different gravitational potentials. So the clock that they were comparing against was in the Naval Observatory on the surface of the Earth, and they were spending all of their time at 30,000 feet. And that also caused the time dilation in the opposite direction. And they needed to describe both of those accurately with both theories of relativity to explain the experimental result that they actually had. And both time dilations together give you the measured time dilation that they had, which was very accurate. And actually, one last thing that's pretty cool. Atomic clocks are so accurate now that you can measure the time dilation from special and general relativity with very minute changes to the behavior of those clocks. So you can you can move an atomic clock at 25 miles per hour and measure a measurable time dilation. And you can also raise it a foot off the ground and measure the time dilation. It's insane. So special and general relativity are doing a fantastic job of describing the universe that we can measure, and we're getting really good at measuring that universe. So the consequence of this time dilation, one consequence of it, is gravitational redshifting. And so there's a redshift that we've talked about in physics for a long time, which is the Doppler effect. And so that you can imagine as the sound of a siren as a fire truck goes speeding by you. The frequency goes up as it gets close to you, and then after it goes by, it has a shift down in frequency. That's just the Doppler effect of moving things. But there's also a redshifting that's caused by gravity because of that time dilation and the changing of clocks as you go into a potential well. So as you move out of that potential well, remember, stronger gravitational fields slow down your clock. So as you move out of that deep gravitational potential, if you're traveling off the Earth, for example, your clock starts to tick faster and faster. And so when you look at a light wave, that period changes, and it causes the frequency of that wave to look like it's getting lower. To look like the wavelength is getting longer. The period of that wave is getting longer. And so that's very important for making astronomical measurements from things that are very, very dense objects with high gravitational potentials. So here's a black hole, for example. If there's an accretion disk right around this black hole emitting all kinds of light, you have to account, if you want to know what the actual frequency of the light when it was emitted from the accretion disk was, you need to account for the redshifting that happens to that light wave as it moves out of the black hole's gravitational potential. So the equivalence principle was the 1911 paper that starts to kind of continue that notion of the equivalence principle for gravity. And he made the jump that not only were freely falling things in an inertial frame, that uniformly accelerating things are indistinguishable from stationary ones in a gravitational field. So you can't tell the difference between sitting on the ground in a box and being in the box of a rocket ship that's accelerating at 9.8 meters per second squared. And that was another leap. I mean, it seems kind of natural. In an elevator, you feel when it's going up, you feel like you're getting a little heavier. Obviously, the gravitational field of the Earth is not changing. It's just you're undergoing an acceleration. And Einstein said not only is that similar, it's identical. It's experimentally indistinguishable in that little box, whether you're on something, you're in a gravitational field, or you're just undergoing some acceleration far away from any massive body in the universe. Any questions so far?
Yeah, just to reiterate, like you explained to me after, only if you take 1 point on the person. Otherwise, it's not the same.
That's right. So this is a very local measurement. This is a local equivalence that Einstein was talking about. If you imagine having some very tall skyscraper, some hollow skyscraper that you're inside of, and you're trying to tell if it's in a rocket ship or on the Earth, you can do very long measurements of the trajectory of particles. If you went to the top of it and dropped it, do those particles travel in exactly a straight line, or do they have some angle that they're falling in because of the Earth's curvature, the curvature of the gravitational field? So that would be a non-local measurement, and you could start to distinguish things if you're not in a uniform gravitational field, if you're in a spherical gravitational field like the Earth creates. But the equivalence applies to very local measurements, but it still is incredibly important and has a lot of implications. One of those implications, oh, sorry, yeah.
Einstein didn't know that the universe was expanding at an accelerating rate, although he kind of suspected it. I think he put a mark on his formula and then thought that was a mistake. Well, does this have, on a cosmic scale, is anybody doing any work on the implications of that?
Yeah, so that's actually a huge area of research, particularly for University of Chicago. The Kavli Institute of Cosmological Physics is housed here, and they're doing very extreme measurements of cosmological effects, and one of them is this expansion of the universe and the cosmological constant that Einstein said was his biggest blunder at one point, but eventually he flip-flopped, put it in and out of equations. We think it belongs there, and we think we have a pretty good measurement of it, but it's the idea of dark energy that causes that cosmic expansion, that accelerating cosmic expansion that you're talking about. And yeah, so that is something that Einstein originally had put in his equations, then took it out because it looked like the universe was entirely flat and there was no accelerating expansion, and then it goes back in once we started making measurements and we find that the universe actually is expanding in an accelerating way. All right. So the natural consequence of that thought of the indistinguishability of something in an accelerating frame versus in a gravitational field gives a very deep meaning to something that was only experimentally found to that point, and that's the equivalence of the mass. So this equation here is Newton's description of gravity. It was doing a fantastic job of describing gravity as we see it in the solar system, besides the Mercury's orbit in some ways. So that is the equation for the force of gravity according to Newton, and that little m is the mass of the object that you're looking for the force on. So in our case, it's us, the mass of us. And that seems experimentally to behave exactly like the mass that shows up in Newton's second equation, which says that the force on an object is proportional to the mass and the acceleration exerted on it. Those two m's seem to be experimentally the same, but according to Newton's theories, there was no deep reason for that to be. It was just an experimental oddity. But in making that claim that you can't tell the difference between something undergoing acceleration and something in a gravitational field, that makes those masses fundamentally the same. And that was a nice thing to do. So there wasn't any experimental reason to disbelieve Newton's theories of gravity and Newton's definition of mass. But this was a much simpler way to describe the experiments that were happening. So the last thing that was in that 1911 paper was the first estimates for the effects of gravity on light, and specifically how the presence of something very massive can deflect the straight path of light. So Fermat's principle is just a statement that light will always take the path of least time. The shortest path between 2 points is always a straight line, so people always thought light travels in a straight line. But when you start having time dilation, due to gravity, then the path of shortest time of travel is not necessarily a straight line anymore. And so those two concepts together is what gives you this idea that light probably bends around massive objects as it's traveling to take that path of least time. And so once this paper was out, people naturally started thinking, okay, well, can we measure the deflection of light travel? And so they started thinking about how we could do this. And the most likely way to measure this was eventually thought to be wait for a solar eclipse and look for a star behind the sun being able to be seen for a little bit longer than it should have. So if the sun is traveled far away from that path in between the star and us, that light will be traveling in a straight line. As the sun moves into that path, it's eventually the gravitational effects of the sun are going to change the path of that light. And it could bend the light that's traveling a little bit to the side of the sun back toward us, and we would actually see that star for just a little bit longer than we should have if the light travel wasn't bending, the path of the light wasn't taking a straight line. And so that measurement was done by Eddington, and this was a great success of Einstein's theory. So this was done in 1919. This was after his full theory of general relativity came forward. But it was verifying this thing that was put forward by Einstein a few years prior to that. And today, this is a very important effect for astronomy. We use it now to trace out mass in the universe. So most of the mass in the universe is not actually in baryonic matter. It's not in stuff that glows in galaxies. It's in what we call dark matter that doesn't emit light. It doesn't interact with things that do emit light. So it's very hard to find. And the only way that we can robustly find where all of this dark matter is distributed is by looking for the effects of its mass on the passage of light. And so here is showing the effects of very massive objects in between distant galaxies and us. If you look here, you can see these warpings, these little lines. Those lines are actually galaxies. They're images of galaxies that are behind this very massive, this really massive object here. And that travel of light is getting bent and distorted and causing this lensing effect that we're seeing with things like Hubble Space Telescope. And that gives us a great way of finding how much dark matter is in the universe and how it's distributed. Any questions so far? Yes?
Is that object, are the stars that you see in the middle of that object in front of that object? Or behind it?
Yeah, so in this case here, you can look at this cartoon up here. So this bright object here is what's being shown right there.
Oh.
And then those rings, those distorted objects over here, are that distant galaxy in that cartoon.
And then the stars are actually in front of the object.
So yeah, this is not actually a star. This is a really massive galaxy. But it looks like a star just because it's so far away. So that is just a really spherical galaxy that's in between that more distant galaxy and us.
Okay.
And then we see that gravitational lensing, and from the images, from the exact distortion of those images, we can make very accurate maps of the distribution of mass in that galaxy, which is pretty cool.
So that ring is the single galaxy behind the source of the mass?
Yeah, so in this case, there's this orangish galaxy over here. It's a single galaxy in the back. There's a bunch of different kinds of patterns that you can get that depend sensitively on the distribution of mass in the foreground. So you can get things like multiple images where you can see the same galaxy in 3 or 4 different ways. And it's actually incredibly cool when we can get lucky enough to have some transient, some short duration event happen in one of those galaxies. Because you'll see it, say there's a supernova in one of those galaxies, you'll see the supernova flash in one of the images, and then you'll see it flash in a different image, and then you'll see it flash in another image, because it's a slightly different path length for the light that it's taking in each of those cases. So you can get multiple cases of transient things happening if you're really, really, really lucky, which is pretty cool. All right, so finally, 1915. Oh, yes?
Just a quick, would we not be able to see objects behind that galaxy if it weren't bending the light, would the light just...
That's right, yeah. So depending on the strength of that deflection, it's usually the case that we can't see things behind it otherwise if it wasn't for that lensing. That's right. It's because it's in between the direct path between us and that distant object. So we can't see through it, but because the light's getting bent around it, we can actually see it because of that lensing effect. So that actually happens on a much smaller scale even for exoplanets, which is a measurement that's actually been confirmed at this point. And so if you have the right conditions, so the way that Kepler, for example, detects exoplanets is it looks at a whole bunch of stars, it monitors their brightness very accurately, and it looks for very small dips in the brightness of that star. And those happen sometimes because a planet that happens to be orbiting around that sun in a plane that's edge on with respect to our point of view, a planet goes in front of the star as we see it, and it blocks just a little bit of the star's light and makes it a little bit dimmer. So that's a measurement that's been used on hundreds and hundreds and hundreds of exoplanets to detect them. But there's an additional effect that if you have the right conditions, the mass of that planet can actually cause that light to bend around the planet and make it actually brighter, make the star look a little bit brighter for a while. And so that's a much smaller scale version of this lensing that we can use to make accurate measurements of the mass of exoplanets. So that was just a tangent, sorry. But general relativity, 1915. That was when Einstein put forward his full, complete picture of what the general theory of relativity looks like. He viewed so it was unique in a few ways. One of them is that it's this geometrical description of gravity. And it's a very different way of thinking about the universe than physicists always did before him. So these are a lot of the roadblocks. The puzzle between gravity and special relativity was one of his motivations. One of the things that made it hard, it took him several years to actually get to this complete picture, was that you needed to think about the universe in this non-Euclidean way, in this non-flat way that we always thought about the universe. That involved going to mathematics that were very complicated, and until that time were thought to be just mind games and things that didn't have any physical implications. The distortions, because they happen to both space and time, also made this theory very hard to come up with. You had to come up with a way that you can cause these distortions in both space and time and come up with the consequences of that distortion. And ultimately, Einstein really lacked the mathematical know-how to solve those problems on his own. And so he had these ideas, he had this physical intuition for how the universe should work, but he didn't have the mathematics to describe it. And it wasn't until he talked with a bunch of mathematicians, some of them working on things that were called Riemannian geometry and Riemann curvature, and covariance, and these ideas in differential geometry of non-flat spaces, that it really started to make sense, and that he started to pair together this math with the physical intuition that he had. And so he moved to this tensor description of things. And so what a tensor is really a bit abstract, but I'll try to illustrate it here for you. Scalars in physics are things like our mass. They're a single number that we use to describe some property of an object. A vector is something like a velocity. It's a magnitude and a direction in space. A tensor is something like a matrix. It's a whole bunch of values that are all part of one kind of physical property of an object. We employ them in classical physics to describe things like rotational motion. To describe the proper rotational motion of something, it's not just this simple vector idea. The distribution of the mass matters, and that has some weird physical effects. This is a weirdly distributed mass in an object. That's a T-handle on the space station. And they just start it rotating. And instead of just doing what you may think intuitively would happen, just this very simple rotation around the axis that it's spinning, the weird distribution of that mass, the tensor behavior of that object's rotation, has some weird physical effects that cause it to do this kind of tumbling motion. It's pretty cool. So it was that tensor description of the behavior of space-time that really was the critical leap for Einstein, and then describing how those tensors can transform in different gravitational fields and different states of motion was the mathematical hurdle that he needed to overcome. And once he started tying together that idea of curvature and gravity, things started to make even more sense to him. So there was this thing that we've been talking about, which is the advancement of the perihelion, the closest point of approach of Mercury to the sun. Astronomers were observing that perihelion, that closest point of orbit, to be moving ever so slightly, 2 degrees per century. And there's lots of reasons for that to move. I mean, if it were just the simple orbit on its own, you just had Newton's gravity describing its behavior, Kepler's laws were describing the orbit of Mercury, and there were no other planets in the solar system, you would expect that elliptical orbit to stay stationary. It would just be, the planet would be orbiting around there, and that ellipse would stay very stationary with respect to where we were looking at it. because there's other planets in the solar system, Jupiter's the big bully of the solar system, it can cause some slight changes to that very simple orbit, and it causes that ellipse to slowly rotate over the course of a century. Now, 2 degrees were measured, and specifically 0.72 degrees per century were unaccounted for based on the measurements of the rest of the solar system. And so this was that experimental observation that seemed to bring the existing theories of Newton's laws and Keplerian motion into question. But astronomers didn't really believe, they just thought there was some bias in that measurement. I mean, it's a pretty small number, and it's a measurement over a century that would take what you are predicting here. And so they thought there just must be some mistake in the measurements, and didn't really put much thought into this measurement, this effect. But when Einstein started moving toward this math of curvature, he predicted exactly that extra bit of rotation of Mercury's orbit, and was sure that that was evidence that he was on the right path. And that's when he finally put forward this idea of a geometric description of gravity in a completely mathematically consistent way. And so a nice one-liner from John Wheeler that describes general relativity is that space-time tells matter how to move, and matter tells space-time how to curve. So you can think of space and time as this fabric sheet in 2 dimensions. If you have a marble traveling on that flat sheet, it will move in a straight line. That's equivalent to going out into space, away from any massive object, throwing a baseball, and having it travel in a straight line. Now, if you put something massive on that fabric sheet, it causes a curvature. Put a bowling ball on a rubber sheet, it's going to curve the rubber sheet, and it's going to change the path of motion of that marble when you roll it again. And the same way, the sun, this really massive object in the solar system, distorts the space-time around it. It causes this curvature. It causes this curvature that the Earth is then feeling. It's then moving around in this curved space, and it's the curvature of that space-time that's telling the Earth how to move. And that's how we can get orbits, as we see in our solar system. And the field equations, the final mathematical picture that Einstein painted, is deceptively simple. This is really all of Einstein's field equations in the absence of cosmological constants. This here is a tensor that describes a distribution of energy and mass. And this here is the curvature of space-time that causes. It's a really simple equation, but Einstein himself thought it was impossible to solve this equation for any realistic situation. It turns out that, one of the misconceptions of Einstein's work is that he was incredibly mathematically savvy, and I've hinted at that not quite being the case with general relativity. He didn't know the math or understand the math at first that was necessary to describe relativity mathematically. Another case of his lack of sheer mathematical ability is his notion that this couldn't be solved. It didn't even take a year for somebody to actually come up with a solution. Yes?
A quote from Wheeler.
Yes?
I puzzled over this so long because it seems to me by a simple substitution of terms on its face to say that space-time tells itself how to curve. And the only solution I can think of that is that the second use of matter means other matter. So, does that make sense to you?
Well, I mean, so this is just a simple way to try to start thinking about how space-time interacts with massive objects. It's a nonlinear theory. The presence of a massive object causes a curvature in space-time that then that object actually feels. So that's what I mean by nonlinear
The
effects.
other matter is the matter that's told how to move as a result of that.
Yes.
Yeah, okay.
So think about it in a step-by-step way. You have a flat space-time, you put a massive object there, it curves that space-time. Now you put another object in there moving in that space-time, and it's going to tell the effects of that curvature. That's the way that this whole thing works. But in reality, there's a very, very non-trivial way that all of these things connect. And the motion of the Earth, for example, say, remove the sun, just think of the Earth traveling through space. The Earth is causing a curvature in the space-time that it's then feeling the effects of. And so that's the non-linear effects that make the actual solution of these equations really tough. It's a set of 10 differential equations, if that means anything, to solve all at the same time in a self-consistent way, which is the the real difficulty mathematically for this. Yes?
The nonlinearity near an event horizon is like out of control, right? That's where it
That's
gets
right.
very
So
hard.
yeah, as we get to stronger and stronger gravitational fields, that becomes more and more of an important thing, this nonlinearity. If you're in a very weak gravitational field, which is most of the solar system is in a very weak gravitational field, you can make approximations to Einstein's equations, and you can linearize them, which is basically getting you back to Newtonian gravity. So that's a very common feature of theories, of new complicated theories, is that they need to simplify in some extreme way. And so when Einstein put forward this theory of general relativity, it needed to simplify, in the case of small gravity, it needed to simplify to Newton's equations of gravity because they did such a great job of describing the behavior of the solar system that we saw for centuries. And so, yes, the nonlinearities, they don't matter so much in the solar system unless you're doing very precise measurements, because Newton's gravities, which were linear, did such a great job of describing the solar system's behavior. It's only when you start getting to really extreme gravitational fields that these nonlinear effects are very important, even for just a simple thing like a movement of particles.
Such as for black holes orbiting each other.
As black holes what?
Pardon?
Sorry, as black holes what?
Orbiting each
Each
other.
orbiting, exactly. So without general relativity, black holes would never merge, and we would have never had the great measurement that we made with LIGO. So, like I said, Einstein thought that it was impossible to really solve these equations that he put forward. He just wrote them down on a piece of paper and said, well, this is nice, this is a great description of the universe, but it's going to be hard to actually learn anything meaningful from it. It took less than a year for Schwarzschild to make a solution. Some would call it at the time a really trivial, not important solution to Einstein's equations, but he made it. He did it while serving in the trenches in World War II, which is pretty cool. I complained about having lots of time to think about things at my desk and not being able to do it. He just did it in his spare time while fighting a war.
With bullets flying.
What's that?
With bullets flying.
That's right.
Yeah.
I complain if somebody's talking in the hallway. Schwarzschild put forward the first exact solutions to these equations in what seemed like simple physical system, but it turns out to have really important implications for astronomy. He published it the same year as General Relativity was published, and it describes, what it's doing is describing the gravitational field outside of a spherical, non-rotating body. So if you imagine the sun, for example, ignore that it's rotating. What does the curvature of the space-time around it look like if you ignore the effects of all the planets? That was what Schwarzschild's solution described. I will show you this equation to give you some physical intuition for what it means. So this equation is describing the curvature of space-time in a local way. Notice that there's a time here, an r here, which is a distance away from the center of that spherical body. So this term here is describing the effects on time caused by that massive body. And that other term over there is describing the effects on space. And so if you notice, you can do things that in mathematics people don't like to do. You can divide by 0 by making a few choices for the value of this distance here, this r. And so what does that mean? There's two weird places where you can do that. So one is just setting r equal to 2m. In this case, m is the mass of that spherical body that you're describing. If you put 2m in for that distance, then you make this term be dividing by 0. It's 1 over that term, so then minus 1 power means there. The other problem is if you meant r equals 0. So in both of these cases, you get infinities in this thing that's supposed to be describing the distortions of space and time caused by massive spherical bodies. And what those mean is shown here. So these light cones are something that are in the handout. I'm describing the notion behind these light cones and why they're a nice tool for imagining the effects of the curvature of space-time. This here is showing, so the vertical axis here is time. So as you move up in this figure, you're going through time. And then the distance left and right here is the r distance that's in that equation. This cylinder here is representing a body, a spherical body, and this r is that 2m, that first solid line, and then the very center of the cylinder is r equals 0. So as you travel toward this spherical body, once you hit that 2m, that outer radius, notice the light cone is doing a weird thing. So that light cone is defining how you can move in time. You can't move faster than the speed of light, so you can't move in the left or right direction faster than the speed of light. That's what's making that cone. Once you go past that horizon, once you go past r equals 2m, then those light cones tip toward the center of the black hole. You can't any longer, once you cross that radius, that distance from the very center of the black hole, you can't go back. You can't, there's no way that you can draw a path through space-time that would get you out of that black hole. So that's defining this event horizon of a black hole. And once you pass it, you're stuck. There's nowhere to go but toward the center, which is the singularity at r equals 0. And so some think that this r equals 0, so that this thing where space-time goes to infinity, the curvature of space-time goes to infinity at r equals 2m. That's described in the event horizon. You can do some transformations of coordinates to get rid of that infinity, but there's nothing you can do to get rid of this infinity. So they're a very different kind of singularity, which is a dividing by 0. The r equals 2m is just this point of no return, and that's defining the event horizon of the black hole. This r equals 0 is a consequence of the fundamental assumptions that go into building this solution. It's defining the effects of a spherical body, but it's saying that all of the mass of that spherical body is in the point, is in a very central location, a point of infinite density, which is the singularity of a black hole. So, yes?
So in that fraction 2m over r,
Yep.
when you set r to 2m, so mass, I think, this is a simple mathematical question of my ignorance of what you're doing here. Mass is in certain dimensions and distances are in other dimensions.
Yes.
You just ignore the dimensions?
Yeah, so there's a bunch of g's and c's. So g, the gravitational constant that's in Newton's description of gravity, and c being the speed of light. You could put all of those in to make the units work out, but when people are working in general relativity, they tend to just set all of those equal to 1 and work in these geometrized units. So in practice, there's g's and c's in here that make all the units work out. But when you actually just write down the curvature of space-time in paper and you're working in these analytical, in these on paper form, you just simplify things in that way. Yes?
I'm really in kindergarten math. What is S?
So S is describing just a little path. It's a little distance that's in the local universe. So yeah, I didn't want to go into too many details about the equations. And so if you have more questions, especially after the talk, I'd be happy to give you really detailed descriptions of what this equation is actually saying. But the cartoon picture of it is that this S that you asked about, which is a good question, is just a little distance in space-time that we want to look at the curvature of. And this is describing the time component of it. These are describing the space component of it. Yes?
If a black hole has a singularity at its center, and all black holes have singularities at its center, a singularity has 0 space, as you just showed.
That's right.
Then how can a singularity have spin?
Yeah, so it's not so much the singularity that has spin as the whole space-time itself. So a black hole, this is the approximation that you have a spherical body that's not rotating. But in practice, we actually do think black holes can spin. And so that adds in extra terms into the curvature and causes a different effect in the curvature of the space-time around it. And so it's there's a non-distribution. So the point of infinite density has 0 volume, which is what you were saying. But it can still have spin. And the space-time itself actually has a bulk spin that it's carrying forward. But it's kind of like in quantum mechanics how an electron can have spin. So an electron, in many ways, is also a point particle. We don't think that it behaves in a classical way of having this momentum and this rotation that you can then just tilt in small ways. It's basically spin up or spin down. And so it's kind of that same effect. You can have a point particle that has spin. It's just not. It's just a weird spin, and it's not the kind of classical spin that we think about if we just spin a globe on its axis. Any other questions? Yes.
What about velocity? Wouldn't two objects the same that have the same mass but different velocity have different gravitational fields?
Yes. So the curvature of space-time around these objects is different for every different mass that you have, and this equation does not describe space-time around anything with a velocity, especially in a rotational sense. So going back to the spin of the black hole. But if you have two black holes that are flying toward one another, That's a very different picture than what this is painting right here. So even if you had two non-rotating black holes that were sitting next to one another, these equations don't work. Because it's not just, the curvature of space-time doesn't add together like a lot of things in physics do. That's going back to that nonlinearity. The curvature of space-time caused by one black hole, or by two black holes, is not just the sum of the curvatures caused by each of the black holes on their own. You have to solve the equations, go back to the very beginning that I showed, those field equations, and solve everything forward in a consistent way, having those two black holes there from the very beginning. So that's what makes solving things in general relativity so hard, and why we need really expensive computer calculations to do it properly. Yes?
Did Einstein have a good understanding of the potential existence of black holes before his theory of relativity? What year do people understand?
Yeah, that's a great question.
You know, because it kind of puts it all in perspective. I'm sorry.
No, this is a really important question. So I think I will probably have a lecture that's devoted almost entirely to black holes, to the theory behind them, the history of the people thinking they existed, their experimental verification, the kinds of measurements we made with them up until September 14th with LIGO. But the short of it is that Einstein, part of the consequence of this type of equation is that black holes exist. So just this effect here, just saying that you have, postulating that if you concentrate all the mass of some spherical object at a point, this is what space-time does around it. Now, this actually is a great description of the curvature of space-time around the sun. And when it breaks down is if you try to go inside of the sun, because it's no longer that idea that all of the mass is in a smaller distance than where you're looking at the curvature of. So just saying that you have this solution doesn't necessarily mean black holes exist. It's just saying that your description breaks down once you go inside of the object. What makes the idea of black holes a reality is this event horizon. And if you imagine things being able to travel inside of that little local event horizon, that means they have to travel to the center. That means you have to form this singularity, and that has a physical consequence, and that's black holes. So when you go into very extreme situations where you have like a stellar explosion that compresses the core of that star into an incredibly tiny volume, smaller than its event horizon, then you must create a black hole. And that's what eventually led to all of the ideas of black holes existing, to their search for them, to their experimental verification.
Did Einstein talk about that, though?
Einstein eventually thought about that, but when it wasn't until the Schwarzschild solution and thinking about the physical consequences of it that they really thought black holes were an actual thing that could exist.
Sometimes you get to wonder how, trying to get in his head, I know
Yeah.
it's impossible.
Yeah. So the thing I've been focusing on is that Einstein had a fantastic physical intuition. The math was a bit short compared to the math that was ultimately needed to do all these solutions. And so there was a slow path to the thought process that led to black holes existing and the search for them. And it wasn't until experimental verification that most people were really convinced that black holes could actually exist. Most people thought it must just be a breaking down of the equations, that there must be something else going on that would prevent such a thing as a black hole from being created. And so finally, we'll go back to that black hole that I showed at the beginning. So this is Gargantua. This inner ring right here is tracing out the event horizon from the camera's point of view. This weird effect going on here is all related to the curvature in space-time caused by that black hole. So what's actually being simulated here is a black hole with a glowing standard accretion disk around it. So it's just a disk of matter in a big distributed ring around the black hole. But when that ring goes behind the black hole, that means the light that's being emitted by that accretion disk is being bent in its path. And so the path of that light from the accretion disk behind the black hole is being curved above and below the black hole to cause that kind of other ring that we're seeing from this point of view. So that's the part of the detail that goes into these simulations, is in properly simulating what that looks like. And so this is actually something we do in science as well, is simulate what the travel of light looks like from that accretion disk. Because if we want to simulate if we want to understand the light that we're seeing from the accretion disk of a black hole, where we look at is X-rays. So as matter falls into a black hole, it gets heated up as it gets closer and closer in that accretion disk. That matter is glowing like the filament of a light bulb, but it's such a hot filament that it's emitting in the X-rays rather than in invisible light. And the emission of those X-rays, if we want to understand it in detail and learn things about the black hole, we do it by simulating what the light being emitted would actually do. And so you model the temperature of this accretion disk, which means modeling the emission of light from that accretion disk. And then you model the travel of that light around the black hole to get to us. And then you can get what the light we expect to measure from an accretion disk would look like. And by modeling it accurately, it's how we can get estimates of the spin of that black hole, for example, which is something we do with LIGO, but in a completely different way. So the last thing I want to do before I take any further questions is show you the real simulation that Kip Thorne wanted to do. So this is showing what the actual accretion disk looks like for the particular details of the black hole that was in Interstellar. So Interstellar was dreamt of by Kip Thorne as being a sci-fi movie where every single element of science in the movie was plausible according to current theory. Now the Nolan brothers got on board, the budget got huge, and forces started to, greater than E, started having effects on the movie. So he had to make a lot of sacrifices and a lot of, so he didn't get exactly his dream, but he did the best that he could with what he had to work with. And so if you've watched the movie, there's a lot of talk about time dilation, and it has a very real effect in the movie and how it carries out. To make the time dilation that they wanted for the story, where when they went down onto the surface of one of the planets, the time changed, the passage of time changed so extremely when they go back to the spaceship. To make that time dilation realistic, he actually had to make this black hole spin very, very, very fast. And so one of the effects of an incredibly fast spinning black hole is a redshift in one side of the black hole versus the other. And so over here, it's dimmer because light being emitted from that side is being more extremely redshifted, and this side is being blue shifted. And so if they were to actually show what the accretion disk around that black hole would look like in the movie, you'd have to show this reddening on one side of the black hole. And the directors thought that that was going to be too big of a leap, and people were just going to be weirded out by it. And so he couldn't show it. But he goes into detail in papers. And actually, he has a book that I very highly recommend that talks about all the science in Interstellar. And I've been told that there's a whole section in the back that talks about all of the sacrifices that he made and all of the weird things that he had to get out to make all of the physics really make sense. But it's a really interesting book, and I highly recommend it. So with that, I say just next week I will not be here. Lee McCullough, who is a former University of Chicago grad student and current employee at LIGO, working on one of the actual instruments, will be here to tell you about how LIGO instruments work, how we can use interferometry to make these very sensitive measurements. And this should be a really interesting talk. Here's a picture of him with some instruments to show that I'm not lying. He does actually touch things in the lab. So with that, I'll take any questions, any further questions you have. And I highly recommend your attendance next week to learn more about the LIGO detectors. Thank you. All right, any further questions that I can get to? Yes?
If you could go back to your formula, I think is what is inside the parentheses, that equals 0.
So that is...
With the R, 0, R equals, in the parentheses, does that equal 0? Just
in the parentheses here. So, yeah, when R equals 2m, this equation goes to 0, which is okay. That's just multiplying dt by 0. But this equation also goes, this parentheses also goes to 0. And this is a 1 over 0, so that's where the bad thing happens. That's where you're dividing by 0 and getting infinities out.
what Einstein today, with all of the power of computers, would he have come up with even more discoveries than he did?
I'm sure he probably would have, yeah. So part of the limitation for coming up with solutions to these equations was that they were confined to do them on paper. And that's really hard. And so, yeah, I think if he had the full computational power that we have today behind him, he probably could have, if he collaborated with the right people, I don't know, maybe Einstein would have had a very different life. He would have gone into be a programmer or something. But if he had gone a similar route that he did back then, and he had some friends that could write some computer code, I'm sure he could have done some very cool things.
Quiet, please.
Any other questions? Yes?
Are you going to go into the parametric and the ring singularity?
Oh, okay. I hadn't planned on going into the details of that. When I talk about the measurable effects from gravitational radiation, Spin is very important, and so I could definitely spend a little bit talking about the Kerr solution, which is the slight modification to the Schwarzschild solution that accounts for the spin of this object. I could probably go into a little bit of detail about that.
I understand those black holes that merge are going spinning extremely fast.
So actually, we think they're not spinning very fast. So the first paper that put out on GW 150914, the only constraints we could really put on the spin of the objects is that they weren't high and aligned with the orbital angular momentum. So we think that they're actually not spinning that fast. But we do expect some black holes to be spinning very fast. And we're really looking forward to getting some gravitational wave signals from binary black hole mergers with lots of spin. Yes? Yeah, sorry.
Going back to those first papers, 1911, equivalence, was it mostly Einstein's intuition, or is there a mathematical structure behind it?
That's mostly intuition. It was intuition. I mean, making those jumps that an observer probably wouldn't be able to. An observer can't tell the difference between being in a state of free fall versus being in a state of zero gravitational field. Those were driven by his intuition, and so it was the intuition of effects like that that eventually led him into the mathematical description in 1915. So he wasn't able to come up with his full framework until he was having conversations with mathematicians working on this curvature and looking at the math of his tensor equations and things, that it all actually came together and made sense completely. Yes?
Are we still making great mathematical breakthroughs in understanding black holes? Or are we kind of in a stasis?
There is an effort to come up with different descriptions of black holes. So one thing that people try to do is explain away singularities. So you can make the jump that space-time starts to behave in a different way once you start getting in incredibly extreme scenarios. And there's actually some kind of negative pressure that forms that keeps that singularity from forming. So that's an example of how mathematically work is being done to describe black holes in different ways that may or may not be more closer to reality.
Like a super physics or something?
It's the same physics. It's just a description of gravity. And particularly the metric is the thing that I showed there. That equation here is a representation of the metric. And so people mess around with the metric. They mess around with the details of things around very dense objects and try to come up with ways to create negative pressure that prevents singularities.
Another Einstein to do something?
So the main problem, so what Einstein spent the rest of his life working on, primarily was trying to take this picture of general relativity, of how gravity behaves on large scales, and make it jive with how things behave on incredibly small scales. So quantum mechanics is probably the only theory that rivals general relativity in its beautiful description of the way physics actually works. And it behaves in a completely probabilistic way, as opposed to general relativity, which is a completely deterministic way. You put down the equations, you put down some initial conditions, you can guess exactly what's going to happen. Quantum mechanics, everything is probabilistic. There's no determinism. You can't say with 100% certainty how anything is going to behave. And so it's giving those two very extreme pictures to meet in the middle. That's that Einstein was really pursuing for the rest of his life. And we're probably going to need another Einstein to really make all that work. Yes? So I can take one more question. Behind, in the back there, since I haven't heard from you. Yes? Yes?
I noticed on your handout last week that there were 3 solar masses lost in the merger of the 2 black holes.
Yes.
Is there a layman's explanation for how you can extract mass from infinitely dense objects?
So I can't even give you a great non-layman's description of how you lose energy. So we actually don't have analytical equations that describe how energy is extracted in the form of gravitational waves from the object. We have to actually fit to numerical relativity simulations to describe that. So in practice, what's happening is you have 2 massive black holes. They merge together. They create all of these gravitational waves. Those gravitational waves carry energy away from that process. In order to carry out energy from that process, you have to extract energy out of the system itself. And so you can extract energy, you can extract mass in the form of energy. That's what happened. It actually emitted 3 solar masses worth of gravitational waves in terms of energy. So it outshined, if you convert that number into energy, if you were to make it instead in light, it would outshine the entire universe for the course that we had detected it. So it was incredibly a very, very, very energetic event. But the details of how you actually can go from the idea of two black holes merging and come up with the number in terms of the energy that it emitted is not trivial at all and very hard to describe. So it's not very satisfying, but sadly that's the... All right, so I think that'll wrap up today. Thank you.